Hello, everybody. Welcome. Whoa. Using my classroom voice when mic'd is a problem. So welcome to the 9th installment of the 2018 Bevan Symposium. I'm Chris Anderson. I'm an economist here in SAFS, and today we're pleased to welcome William Cheung. William Cheung did his PhD at the University of British Columbia and stuck around as faculty. He is now an associate professor and the director or co-director of the UBC Nereus program. Let's see, his research is focused primarily on the interaction of climate change and fishing and how the changes in ecosystem services that will occur with climate change affect people and the best way to manage people. He's exceptionally productive. He's published over 150 articles, including many in Science and Nature that have given us a sense of how climate change is going to affect fishing and many other things. And he's been a lead author in the IPCC Working Group 2, which is the vulnerability of socioeconomic and natural processes working group. And today he's going to give us a fairly broad overview of how climate change is going to affect seafood production and what we can do about that as managers. One final reminder before I hand the mic over to him, please silence your phones, and there's a little button on the side, or if you're like me and you've just managed to kill your battery on the way down the stairs, you're safe too. There we go.
Thank you very much. Thank you. Hi. Can you hear me okay at the back? That's good. So first of all, I would like to thank Judy and the organizer for inviting me to speak in the Bevan series. It's such an honor and pleasure to come down from Vancouver to Seattle and particularly University of Washington to speak with colleagues and friends in here. I've been in University of Washington for a few times for meetings and meeting people, but I've actually never been to the Fisheries school, so it is also a really good opportunities for me to meet with people and visit the school and get to know more about the works that are being done in here. Yeah, just an anecdote. Thanks for the introduction. One thing that after I got my PhD in UBC, I actually spent a few years as a lecturer, faculty member in the University of East Anglia. And that's right at the time when ClimateGate happened. So if anyone knows about the ClimateGate, it's the release of information from the university's famous climatic research unit, and the skeptics framed that as scientists trying to manipulate data to create a hoax about climate change. I was actually working in that office when that happened, and that actually connects me to really give me a real experience about that climate change, that the science of climate change is not only a scientific problem, but then it's so much connected to the society, the politics, and that we really need to we have much bigger responsibility as a scientist in not only generate the science, but then also communicate that and also participate in supporting some of the policies, discussions regarding climate change. And that's something that I will try to touch on in my talk today. It will cover some of the science, understanding about the impacts, as well as some of the things that we can do in terms of informing policies, as well as developing solutions to tackle this problem. So before going into my talk, I just want to get a little bit more introductions about my group in UBC. So in case you are interested, you are always welcome to get in touch with us and maybe even visit us in Vancouver. It's pretty close by. So I'm leading the group called Changing Ocean Research Unit, which basically try to tackle the challenge about changing oceans, global change, and how that affects ecosystem and fisheries, using models and scenarios and developing database to do that. And we do both science as well as trying to communicate our science to inform policies. And as as was introduced, one of the big programs that I'm leading, co-leading is the Nervousness program. And I'm co-leading with actually one of the colleagues here at University of Washington in the School of Marine Affairs, Yoshitaka Ota. So he is a social scientist while I'm a natural scientist, co-leading the program. So this program is an international interdisciplinary program trying to predict the future oceans. So if you want to know more about that, which is a really exciting and interesting program, please visit our website at nervousnessprogram.org. And I want to acknowledge all the contributions from my team first, because the works that I'm presenting is not my personal work. A lot of it is through collaboration with the colleagues, particularly with teams of students, postdoc, and researchers in UBC and elsewhere with other collaborators and partners. So I want to thank them for generating those science so that I can put together this talk together. So specifically today, there are three components I will talk about. First of all, I will talk about some of the science about how drivers, particularly human drivers, that affects the oceans would then impact fish and fisheries. After that, I will try to draw from the scientific understanding of these drivers and try to develop a vision of what the future of fish and fisheries would be like, particularly under scenarios of climate change, using some of the modeling tools that we developed. And then I was always blamed of giving really dooming talk about how climate change will trash the oceans and that our children will have no fish to eat anymore. So I promise I won't leave you with that feeling. I will try to talk more about the solution space and what are the opportunities that are out there that we can pursue to help resolve some of these issues. There will be still remaining challenges, but at least there are something that we can do now to deal with that problem. So I want to start off with three sets of numbers: 1 billion versus 9.7 billion, 700 billions versus 100,000 billion, and 0.2 billions versus 700 billions. Try to think about what these three sets of numbers represent. I guess most of you may have guessed one way or another. This represents three kind of indicators of development of our society. In the last couple of centuries, it showcased the amazing rapid development of our society. From a couple of centuries ago, where we have only 1 billion people on our planet, now and projecting into the next couple of decades, we will have almost 10 billion people. Our economic growth is amazing. Our GDP has grown more than 10 times during this period. But in doing so, in driving this economic growth, part of the reason for that is our ability to utilize new source of energy, and particularly fossil fuel, and also accompanied with that vast changes in our way of using our land and ocean. And all of this contribute to emissions of greenhouse gas, carbon dioxide, and other greenhouse gases. And so the last set of number basically is the cumulative carbon emissions from human activities and the projected emissions by the next few decades. And all these changes has transformed our planet substantially. And that leads to massive changes in ecosystems, biodiversity, as well as our way of interacting with nature. And that includes the oceans. And fishery is one of the good example of illustrating that. This is a figures that shows the global fisheries production. This is the versions of the data set from the CMR's project, Global Fisheries Catch Data, where they take the United Nations statistics and then add some value to it by estimating those catches that are not reported in the national statistics by different countries. But more or less, the story is that fisheries catches increase from 1950s to around 1990s and then level off or in some cases decreases. At the same time, fishing effort, our ability to catch fish continues to increase. We use bigger boats, we have better technologies to go out fishing. But particularly if we look at the period during the last couple of decades, even though our ability to catch fish continue to increase, but our fish catch do not increase. So that is a first indications that we are at the level of at least being at the maximum capacity of getting fish from the oceans, at least for the traditional fish stocks. There has been some progress, a lot of progress in developments of aquacultures and in the oceans for producing seafood, mariculture, so farming of shellfish and fish. And that expanded a lot, particularly in China. But even adding that to the equations, we can only see a leveling off of global fisheries production during the last couple of decades. And we also know that based on various estimates, some of it from this school, that many fish stocks in the world are also overexploited. And that's one of the reasons why we cannot get more fish from the oceans, because we are already fully or overexploited the fish stocks. So the question is what the futures of seafood production would be like. Can we continue to increase producing more seafood, particularly in the face of continuous increase in populations, economic wealth that often bring together a bigger demand for seafood, or that we need to find a different pathway for our seafood production in the future. Aquaculture, would that be a solution? And adding to this uncertainty is the whole issues of climate change, because climate change is certainly not only affects the atmosphere, but also affects the ocean. Large amounts of carbon dioxide that are emitted by human activities are absorbed by the oceans. More than almost 30% of CO2 go into the oceans. And that's majority of the heat energy generated are also going to the oceans with the high heat capacity of the oceans. But in doing so, with the oceans absorbing so much of CO2 and heat, it is also changing the property of the oceans. It's getting warmer, with more CO2, it is getting more acidic, and also there is a robust data set that shows, that the global oxygen content in the water is also decreasing. And all of this is expected to continue given our trajectories of CO2 emission. So this is a figure that shows the projected changes in some of the ocean variables that are important, particularly for marine life in this century. I want to highlight the two different trajectories, which I will talk about in some of the slides and the things that I talk about in my presentations. The red line represents the high emissions business as usual scenario, or more technically, it's called the representative concentration pathway, X.5, or RCP X.5. So that represents a business as usual high emission scenario, as opposed to a blue line, which is a low emission, strong mitigation scenario. So meaning that our world is able to get together and do really effectively in mitigating carbon emissions. So that's the low emission scenario, or sometimes it will be referred to RCP 2.6. So given those trajectory, we really need to think hard of how we can alter our society so that we can actually go into a sustainable pathway with possibly low emissions and also other things that we can change in order to reduce the risk of impacts of how these changing ocean environments will affect our fish and fisheries. And in order to do that, we cannot stay in our disciplinary comfort zone. We really need to join force between disciplines and could develop this pathway that can cut across from the ocean science to biological science to social and economic realm. And we need to understand, for example, how changing ocean environment conditions such as temperature or oxygen may affect the biology of the organisms, how that would affect population dynamic, trophic interactions, and how that interact with economics of fishing, where the fishermen will go fishing and what kind of fish they would get, and how all of this will interact with broader society changes. Food production from land, food production from agriculture, or changes in energy use, other global environment policies, and how that interact with one another. And by doing so, we may get some insights of what pathway would be likely to take us to a more sustainable pathway for the oceans and fisheries. And the first step of doing so is to identify what are the key drivers of changes in the oceans, particularly for fisheries, so that we can then understand with these changes in drivers expected for the future, how would that then affect our fish and fisheries? And that could then inform our scenarios of what will be like in the future and get ourselves prepared of what our future will happen. So this is an example of a study that highlights the effort to attribute the different human drivers in affecting fisheries productions. The way that we did this analysis is that we take the fisheries catch data from around the world, particularly separated by large marine ecosystems, as indicated by the line along the coast, and then try to use statistical method to identify what are the key variables that are related to changes in the fishery productions in these different regions. So we separate into two kind of factors. One is what we call top-down factors, the fishing factors, fishing effort, and then the bottom-up, so the changes in ocean productivities as indicated by the core field A or primary production. And the third one is a mixture of, and the third one is the sea surface temperature, the changes in environmental temperature. And what we find is that both fishing effects and changes in the environments play a role in affecting our fisheries productions in the past. And that it varies between different regions, and it's very likely that it's because of the different characteristics of the ocean basin, as well as the history of the human activities in those ocean basins. So for example, like take Australia, it is identified as somewhere that is strongly affected by fishing. And part of the reason that we identify is that Australia water is oligotrophic, meaning that it is limited by nutrients. So, but then all the historical, it is really recent exploitation, with really recent exploitation history of fisheries. So the fishery resources is in the phase of development and expansion. So fishing in that particular context play a much bigger role in affecting fisheries catch compared to bottom-up effects in a nutrient-limited oligotrophic system. So that provides the take-home message from this is that we need to account not only for fishing, but then the changes in the ocean productivities in thinking about how things would affect future ocean production. And getting into a little bit more details, it is not only a relationship, a causal relationship that we see from these different factors, particularly for the ocean productivity factors, but that there are clear causal link that can relate to theories about how changes in ocean productivity will affect upper trophic level production. So we take information about different productivities in large marine ecosystems, and then try to identify what are the mechanisms that would best explain the changes in the different productivity in different ecosystems. And what we find as expected is that primary productions play a big role, but then it doesn't explain a lot of the other variants or variations in the primary upper trophic level productions. Many other components that would affect the level of fish productions in different systems is related to the amount of the efficiency of the ecosystem, whether when energy transfer from one trophic level to the other, whether it is very efficient, meaning that it has a high trophic transfer efficiency or not, or how much of the energy actually partitions between the surface layer versus the bottom layer, because the ocean is not only a surface. It is actually a three-dimensional habitat where there are clear separation of different systems across the water column. So by better partitioning these different set of ecosystems along the water column, it also helps us to explain quite substantial variations in the different productivities between large marine ecosystems. And one aspect that we can learn from this exercise is that besides understanding the mechanisms driving lower trophic level productions to upper trophic level productions, but also the fact that these variables, such as trophic transfer efficiency and the flux of energies from the surface to the oceans, are also dependent on the ocean's conditions. We find that the best models that can explain the different productivities, fisheries productivities in different ecosystems relates to having a temperature-dependent trophic transfer efficiency. Some of our newer work suggests that with warmer oceans, it may actually decrease trophic transfer efficiency. So less energy will be made available from primary productions to fish. And so is carbon export, which is a much more complicated process that would affect the currents and mixing, stratifications may also affect the flux. So all the key message from this is that changing oceans will alter the ecosystem structures, affecting how much fish we can get given a certain amount of productivities. And at the same time, primary production is also changing under climate change. And we are expecting that there may be a decrease in primary productions in the next century. And that's actually one of the consistent projections from all the Earth system models with the climate and ocean component in it. So we may be also seeing less primary production in the oceans. So with less primary productions, changes in trophic transfer efficiency and carbon flux, we will be seeing potential decrease in fisheries productions, which I will come back in a later slide. But biomass is not the only things that we care. I mean, so there are 3 dishes in here. Those 3 are Chinese dishes. I grew up in Hong Kong, so seafood is a big part of my culture. Here we have a coral trout, which we only serve in big banquet, wedding banquet and things like that. This is a everyday fish, flat fin beam. When I grew up, my mom used to fly this fish every day for us. It's getting expensive now because it's overfish is less available now. And squid is totally something different. And there are also different nutritional values associated with these different species too. So just understanding the changes in biomass may not be sufficient for us to understand the future of fish and fisheries and how that link to our society. We also want to know how different species may respond to climate change. And we know that different species would respond differently because of their biology. Some species are more affiliated to warm water, some species are more affiliated to cold water. But one general principle is that fish is a warm-blood, cold-blood organism. So when temperature, they only survive in a certain range of temperature, and when temperature becomes too hot or too cold, their body performance decreases, and at some point, they just cannot survive and die. And different species will have different temperature tolerance and range of temperature that they prefer. And I think from other speakers in this series that I think it must have covered this quite eloquently, that when species exposed to changing ocean conditions, like a warmer temperature, then they won't stay put, most of them, particularly for fish, because they are mobile animals. So they respond, one of the most widely reported response is that they would shift their distributions so that they can pack their bag and find somewhere cooler for them to live so they can survive or do well in the temperature, in the habitats where it is within their range of temperature that they can survive. So in general, they may move to higher temperature, higher latitude or deeper water, or area where they can find cooler refuge. And in fact, this has been reported for hundreds of species, even thousands of species around the world, from plankton to fish to invertebrates to mammals. And they're shifting tens to hundreds of kilometers per decade in the last few decades of that already. So it is not something that is theoretical, it is already happening. And right now, with the ability to gather a large data set, we are able to also test this hypothesis about how important temperature is in affecting these patterns, global patterns of species distributions and biodiversity. So our team gathered together various global databases on marine biodiversity, from phytoplanktons to up to marine mammals. And we characterized their thermal habitats by the temperature that they prefer and the range of temperature that they can tolerate. So this is plotted in here, where this is the temperature that they would prefer. And then this is the range of temperature that they can tolerate. So some species can only tolerate a really narrow range of temperature, like a few degrees Celsius, while some can tolerate like 20 degrees Celsius. But in general, what we find is that there's a clear pattern that tropical species and polar species that prefer warm and cold temperatures tend also to have a much narrower range of temperature tolerance range, while intermediate range species have much bigger tolerance range. And that if we use these two informations combined with ocean temperature, we are surprised to find that we can explain more than 70%, even higher than, of the global patterns of species richness, from phytoplanktons to marine mammals. And so it means, it suggests that, and we compare that with other hypotheses of explaining patterns of biodiversity. And still, temperature is one of the highest, most likely hypotheses explaining the global patterns of biodiversity, marine biodiversity. So the take-home message from this is that with that strong relationship between temperature and patterns of biodiversity, it also highlights the fact that when temperature changes, the whole patterns of biodiversity as shown in, or species richness as shown in the upper figures is likely to shift. And that obviously will have impacts on fisheries, because fisheries is basically fishermen go out to the fishing ground and fish for what they want, what they are available in the oceans. So we, in this particular analysis, we look at global fisheries catches and then try to quantify the relative importance of warm water species versus cold water species. So warm water species is redfish, cold water species is bluefish. And we look at that for each year, for each region, and see how these would change over time. So if we use an index called the mean temperature of the catch. So when fisheries catch is dominated by cold water species, it has a low mean temperature of the catch. But as there are more warmer water species getting into the fisheries, the mean temperature of the catch increases. And this is for temperate fisheries, and this is for tropical fisheries. And what we find is that for temperate or high latitude fisheries, as expected, in the last few decades, when the ocean warms up, with the gray line on top, the sea surface temperature, the mean temperature of the catch actually increased, meaning that it is catching more and more warm water species, because species are shifting their distribution. But then for the tropical area, when we first look at our results, we were surprised to see that we don't find that uniform trends in mean temperature of the catch that follows sea surface temperature. But then after looking at our hypothesis again, it does make sense, because the tropical area is kind of the hottest place on Earth, or on the oceans. So when the more cooler water species leave the tropics, it leaves behind those species that can sustain or survive in the warmer water. So, so that it explains why there is that flattening of the mean temperature of the catch. The next question then is, what would happen in the future if temperature of the oceans continue to increase? And particularly in addition to that, other ocean variables such as oxygen, primary protections will continue to change. So the next set of challenge for us to actually develop that pathway for future ocean sustainability is to better understand the future of this sector of fish and fisheries. And to look into the future, we don't have a crystal ball, so we cannot use that to just fortune telling what would happen in the world oceans. But we have some scientific tools, like modeling tools, that allow us to put together our latest understanding about the drivers of changes, the mechanism of changes from species and productivities, into a modeling mathematical framework that allow us to make some projections of future changes in fish and fisheries. And this is a framework that, of a modeling framework called dynamic bioclimate envelope model that myself and my team has been developing in the last decade or so. I won't get into the details about this. I'm sure Andre would like to get into all the equations in the model, but we can talk about that maybe in dinner or during after the talk. But just take this for granted that these models will account for changes in ocean conditions, the physiology, habitat, and population dynamics of different species. So just showcase some of the results that are generated from this kind of modeling tools, and take the example of the Pacific coast of North America. It projects changes in the abundance, distribution, and potential catches of species. And this can be represented, for example, by the distribution centroid of a particular species, like the Pacific halibut, that distributes along a longitude and a latitudinal range. And the different points represent the projected changes and trajectory into the future. In this case, the Pacific halibut is projected to shift further north and a little bit of west. And one can compare the trend trajectory for different species like salmon or sardine or mackerel or rockfish. If you repeat that for lots of species, then one can try to look at the aggregate community changes and the implications for the fisheries in terms of species compositions and potential catches, as well as kind of the mean changes of the system over time, which is highlighted by the black line. So in this case, the communities may shift by around 500 kilometers per decade under the RCP 8.5, so high emission scenario here. And with this, we applied this to around 1,000 different species of fish and invertebrates around the world, or commercially exploited fish stocks, and try to quantify the potential implications of climate change on future fisheries production. So in this case, on the horizontal axis here, that's the atmospheric warming. We use that scale because that's something that policymakers would resonate. People talk about whether we want a 3 degrees Celsius world, or 1 degree Celsius world, or 1.5 degrees Celsius world, as depicted by the Paris Agreement. So that's atmospheric warming, while the vertical axis here is the maximum catch potential, or MCP. So that's kind of the theoretical productivities of the fish stocks. And what we find is that with the current our modeling framework, we project a decrease in potential fisheries catch of up to around 10% under a 4 degrees Celsius warming scenario. So that's more or less a business as usual scenario, or high emission scenario. While if we were to be able to reduce per unit for each degree Celsius of atmospheric warming, we can actually save 3.4 million fish per year. So we can actually get 3.4 million fish from the oceans more compared to a 1 more degree Celsius warming world. So there's a substantial benefits by reducing global warming here. While the level of species turnover, meaning changes in species compositions, also scale with atmospheric warming. So in this case, if we reduce per unit degree Celsius of global warming, we are able to reduce the level of changes in fisheries species compositions by around 7%. And the changes are also not uniform. It's vary in different parts of the world. So we look at it at a spatial point of view, particularly looking at the potential changes in the mean temperature of the potential catch potential in different countries' exclusive economic zone. We also look at it from the point of view of the economic side. So meaning that how much fishermen can get from selling their fish, whether the changes in catch will actually affect more or less in terms of the amount of money that they can get by selling their fish after they go out fishing for a year. What we find is that the tropical area will be the highest, the hotspot for impacts, where you see a substantial decrease in potential fishery catches, as well as a decrease in potential revenue from the fisheries. While high latitude regions, for example, such as Greenland, is going to gain because species are shifting forward, and that they will be seeing more resources in their own waters, and fishermen will be able to get more benefits by selling the increased catches. And one thing that we find is that the economic impacts may actually be higher than the biomass impact because some of the species that are most affected may have higher economic value. The price is higher compared to those that are gaining. So that's why in this particular analysis, we find that the effects on fisheries revenues is actually 35% more compared to the effects on fisheries biomass. And just when you wonder why the tropical area is the highest hit area, and one of the reasons is that species are shifting away from the tropical area, and that some of the models are projecting a decrease in productivities, primary productivities in the tropical area. But when you look at it from the point of view of the habitats, what we find is that when we quantify kind of the habitats based on temperature, oxygen, acidity, and net pie production, we find that the tropical area is an area where there's that emergence of novel habitat, meaning that the combinations of these different environmental conditions is new to the whole world oceans compared to last few thousand years. If a species is not able to adapt to those kind of novel habitats, at least that's what our assumptions is in our models, they would be impacted. Their productivity will decrease, they may die, more of them will die, and so you will see that big impacts on fisheries and fisheries catches that I showed in my earlier slide. And not only that the oceans will be affected, it also magnified by the fact that the land also has similar patterns of impacts. This is a study in collaborations with, led by my colleague Julia Blanchard in Tasmania, University of Tasmania there, that combined various model projections, including ours with colleagues who do aquaculture projections under climate change. And in this case, what you see is that some of the countries that will see large impacts on both oceans and land, like West Africa, Southeast Asia, they are the most highly impacted in terms of food productions, given the high emission scenario. So that poses an even bigger challenge for them, for countries in that regions to actually adapt to those changes. On top of that, their nutritional dependence on fish may also be most important for people in those regions. So this is a study in collaborations with, it's led by colleagues in Harvard who work on fish nutrition, and colleagues here in marine affairs. Eddie Allison is also one of the colleagues who is collaborating in this work. We identify countries that are most dependent on fish for nutrition, such as particularly for micronutrients, such as omega-3 fatty acids, zinc, iron, and overlay that with the projected changes in fish catches under climate change, the map that I showed you earlier. And the key message from that is that, unfortunately, they map really well. That the blue color, which shows a large decrease in catch potentials, are also areas that are highlighted as highly dependent on fish as a source of micronutrients for their diet. So if we assume that decrease in fish in the future means a decrease in supply of those seafood micronutrients to these populations, there's a high risk that these populations will suffer from health issues because of malnutrition. And not only that the tropical and developing countries will be affected, but there are also vulnerable populations even in developed countries, such as coastal First Nations in British Columbia, just up the coast in here, where they are nutritionally highly dependent on seafood. They're culturally also very dependent on particular species as well. And our model projected that many species that are currently dependent will be strongly affected by climate change. So the circle represents the projected decrease in the potential catch of those species. And so that poses particular challenge for them to adapt to some of these impacts. And there is, later when we talk about solutions, we are actually trying to develop some projects that identified pathway that they can, these coastal First Nations can adapt to some of these impacts. And besides challenging the direct supply of fish, these kind of changes in the oceans also challenge the way we govern the oceans. So shifting this species distribution may affect the effectiveness of protected areas when species are actually moving away from that area, or that species crossing political boundaries may actually generate conflicts or issues with managing transboundary fish stocks. And those kind of things are actually happening now. It's not, again, something that we expect to happen only in the end of the century. One of the very good example is Atlantic mackerel in the European waters, where the shift in distributions of Atlantic mackerel in the last few years towards high latitude regions actually leads to the gain of resources in Iceland and Faroe Islands. But then these countries unilaterally increase their quota, leading a big international dispute between different European countries about the sharing and allocations of these important fish stocks in European waters. So that's a really good key example of how changing species distributions and the climate change may challenge transboundary fisheries management. And it's happening all around the world, and I think particularly in US and Canada and Mexico, we are sharing a lot of the transboundary fish stocks. And this is the work of one of my PhD students. It highlight that these are the potential catches of the current transboundary fish stocks, such as Pacific halibut, salmon, and it shows that potentially in the future there may be gain and loss between different countries, where Canada may be gaining while US may be losing some of the catches. And that throws a really big uncertainty about whether the current treaties, like Pacific salmon treaties or the halibut treaties, are sufficient in accommodating this kind of shift in distributions and potential benefits by different countries for these transboundary fish stocks. And then for marine protected area, we know species are shifting their distributions. And if we think about the magnitude of these species shifting their distributions relative to the size of the marine protected area. So if a species is shifting so much that it is much bigger than the size, is much further than the size of the MPA. So in this case, the centroid shift of the distribution of the species is much bigger than the diameter of the MPA. Then it probably that shifting distribution of the species may challenge the marine protected area in capturing the species distribution range of these animals. So if we take the example of the US West Coast, this is the figure that I showed you earlier, and then overlay that with the size of the MPA. So this is the theoretical size that we need in order to capture the range shift of the future. For 50 years climate-proof MPA or 100 years climate-proof MPA. So that's pretty big size. And then let's compare that with the existing MPAs in the West Coast. So let's look at kind of the first percentile, 50 percentile of the area of the MPAs in the US. Yeah, it's there, but it's just a dot here. So we cannot see it yet. We still cannot see it when we increase the size to 75 percentile of all the MPAs in the West Coast. And we can only see it when we include one of the biggest MPA, the Pacific Monument. So it highlights the challenge that we are facing in terms of MPA design. But the US is not the alone. I mean, it's not criticizing the US in terms of the size of the MPA. It is the same everywhere in the world. So we take the whole global MPA database and look at their size and compare that with the range shift that are projected all around the world. Again, only around less than 2% of the MPA will be at the size that would be able to capture the average range shift across different species. And I'm not advocating that we need to have a huge MPA everywhere and protecting all the oceans. But it is an indication that we need to rethink about the way we design and manage our MPAs, whether we need big MPAs or we need a network of MPAs that can help to mitigate or help to adapt to this changing species distribution. So I promised that I would talk about solutions. So that will be my final components of the talk. With all these changes, I know it's kind of doom and gloom. Species are changing, it's impacting fisheries, not only in the tropics, but then also in high latitude, in vulnerable communities. So we wonder whether we still have fish to eat in the future and who will get those fish. But I think there's good story in the last few years. First of all is the Paris Agreement, which highlight that the world has a consensus that we need to tackle climate change together. I know the US is I'm stepping back a little bit, but I think, but I think that's the trends of the whole world. That's if you look at historical developments, and I think that's it will be inevitable. I think it's unstoppable. So we have a goal, 1.5 degrees Celsius, but how to reach that goal is a big question now. And one thing that is important to highlight is that the oceans actually play a big component in meeting that Paris Agreement. So this is a study by Natalie Gallo, one of Liz Leffen's students in Scripps. They look at across all the national determined contributions that different countries propose in their aspirations of how they can meet the global global climate targets. And what they find is that surprisingly, 70% of those mitigations involve the oceans, and it can be broken down into climate adaptations only, or adaptations with mitigation. Some of it may involve blue carbons and things like that. So that highlights that the oceans can play a really big and important role in the whole climate change discussions, which is often overlooked. So we actually recently start to tackle this problem about how to solve this climate problem through ocean-based solutions. And it started off with a working group that we had to evaluate ocean-based climate solutions, particularly about the effectiveness and whether they are ready to solve the climate problems now. And this is one of the synthesis figures that we put together. So there are 4 broad-based types of solutions. So one aspect is addressing directly the climate cause, so mitigations of carbon. And one of the highlights that in here is that there are already existing cost-effective, scalable solutions, which is from the ocean, which is renewable energy, like offshore wind farms, that can actually provide substantial contributions to carbon mitigations. Although there are still a lot of other very uncertain, really risky, and still in the lab kind of ideas like ocean fertilization, alkalinization, as well as that, which we need to be really careful in moving forward, because that can have a huge impact on marine ecosystems based on our findings. Another aspect is that there is also a big component that we know are effective, which is protecting the biota and ecosystems. There are already historically a large body of science supporting the effectiveness of those solutions. So those are already tested. They are cost-effective. In fact, they are really low risk because there's big co-benefit, meaning that even they don't contribute much to climate, solving the climate problems, they are good anyway in conserving and managing our resources, such as protecting habitat and things like that. Okay. I want to, before at the very final part of my talk, I want to highlight a few examples that we actually do some analysis of exploring those kind of climate solutions. As an example of how these kind of, how our science can actually provide information to support the further development of those solution options, and how that we can then incorporate that in thinking about the pathway for sustainable fish and fisheries under climate change. The first one is about managing the high seas and in relation to climate change. There's been a lot of policy discussions about management of the high seas, so area outside of our national jurisdiction's waters. And there's been suggestion that by better managing the high seas, or even protecting all the high seas, it can benefit coastal states, because it will build up more fish stocks, and that these fish stocks will actually spill over to the coastal states, where they will benefit by having more fish in their waters. So we test that hypothesis using our models, and particularly add climate change into the equation, and see whether protecting the high sea or better fisheries management on the high seas can actually help reduce climate risk at the coastal state. So these are the four kind of results that we find: high emission, low emission. This is the status quo, kind of heavy exploitation scenarios in the high seas versus high sea coasture. Or we have also a scenario of sustainably manage the high sea. And what we find is that a low emission scenario and a good management of the high sea, or even protecting the high seas, actually can help many of the coastal states to mitigate or balance out the climate impacts. So on one hand, climate change reduce their fisheries catches, while on the other hand, more fish going into the water from the high sea actually increase the productivity. So that would balance out so that they will help to reduce the overall climate risk. But one aspect that we see is that there are still a lot of wet area here, as you notice. As I showed earlier, these areas are those novel habitats, meaning that, at least in our models, the habitat has become so bad that the species will not go there, even there are lots of fish in the oceans. So that's why this is the most challenging aspect of the future oceans, how to help these regions to adapt and reduce their climate risk. Another dimension that we look at is about the habitats, where the better protecting the habitats can reduce climate impacts on fisheries. So we have a case study in the Caribbean, which was done by my PhD student, Ravi, and he looked at the mean temperature of the catch, something that I showed you earlier, for different Caribbean countries, and tried to relate that to changes in sea surface temperatures in these different countries, as well as the quality in terms of the size of the reef habitats in these different countries. So these are only for coral reef species. The overall message from this analysis is that you look at the relationship between these different variables, like sea surface temperature, habitat area. And what he finds is that as you expect, more warmings will lead to bigger changes in species compositions in the Caribbean waters or Caribbean coral reef species fisheries. But then area with a bigger habitat size actually have a lower sensitivities, meaning that you will see less changes in the fisheries in terms of species composition compared to those with a smaller habitat size. So that provides or contributes to an expanding body of literature that suggests that higher quality habitats, bigger habitats actually can help moderate climate risk. And then I probably go through. Basically, that slide shows that there is interaction between climate change and pollution, and so reducing pollutions also reduce sensitivity of species to climate change. And finally, it's about aquaculture, and whether aquaculture can play a role in solving the problem, and particularly for mariculture. So Mohammed, one of my PhD students, tried to quantify whether we have scope for further expanding mariculture. So he looked at habitats that are suitable for farming different mariculture species in the world oceans. And what he finds is that there's still a large part of the oceans that are suitable for farming mariculture species. But that a lot of the limitations for its expansion now is because of socioeconomic reasons. But then mariculture would not be separated from the whole climate change problem, because currently fish mariculture or shellfish mariculture is still dependent on ocean conditions. So what he is doing now is to try to project how these habitats would change over time under climate change. For example, for Atlantic salmon, habitats will be actually, some habitats will become not suitable for farming salmon, while some will be more suitable. So again, we need to rethink whether maricultures can be suitable as further expansions, and how that can play a role in producing seafood in the future, on top of other economic reasons, such as how it may combine or how it may compete with wild capture fisheries. And this particular analysis, where we actually look at scenarios of changes in mariculture and fisheries, capture fisheries. And what we find is that scenarios of expanded aquaculture productions may actually lead to a bigger impact of climate change on capture fisheries because of the changes in potential price of the fisheries. With bigger mariculture productions or aquaculture productions, increased supply without assuming that demand doesn't catch up, it may actually lead to a decrease in price that would actually further draw down the overall revenues of the fisheries. So with that, I think there is a good story that is coming out from the solution aspect, that we already know there are solutions that are available both for mitigation as well as for adaptations. And also that are low regret solutions. So better protecting habitat, better managing our fisheries, those are the things that manager would have to do anyway. And that there's increasing science that suggests that that would be useful for climate change adaptation as well. I think one aspect that we need to think about is how to design these different tools into different local setting. We know that it would be so much simpler or easier if one solution can fit all problems in the world, where we can have this set of solutions that can apply in every part of the oceans, every system. But unfortunately, that's not the case. The problems, particularly in the tropical areas, may likely to need a different set of tools compared to those in Canada or Europe waters. And that one way to do that is actually to involve different regions, different communities to co-design these potential solutions, where we can have these solutions tools and then find a pathway where a mixture of these solution tools will be most suitable for the future of those regions. And one way that we can do it is through the use of participatory scenario development, where informed by the science that I talk about, where we can inform what the future changes in the ocean may be like, but then involving them in trying to design what will be the solutions that are suitable for them in developing or mitigating and adapting to climate change. And in addition, one thing that would be also really timely is that there is a big international demand for this kind of science. There is a new IPCC report that is coming up for the ocean and cryosphere. So it's the first time that the IPCC has special reports for the oceans, and some of the colleagues here, like Anne, is involved as one of the lead authors in those reports. So I think there's a good timing for contributing, bringing this science into that policy discussion as well. So with that, I want to thank the organizer again for inviting me to speak with you about that, this topic that I'm passionate about, and I'm happy to discuss with you more.
All right, we've got a couple minutes for questions.
You mentioned sea level rise and you mentioned aquaculture. And the thought occurred to me what it would do to real estate values if people started discussing what kind of fish we would raise in the subways of New York.
Well, as I think that's highlight the importance of considering these multiple drivers of impacts, where you have, on one hand, sea level rise as challenging coastal communities, and that's posing a really serious threat. While on the other hand, there is these resource changes that are adding on top of sea level rise in the others. And I think that creates a particularly challenging space of developing these solution potential options for them to deal with. And that's not a, particularly for, again, going back to, I'm sure people in the New York or London will be able to deal with that. Like there are key engineering solutions that are available to deal with sea level rise by which country, but not for tropical countries. So again, it highlights the importance that we probably need to focus our resources and effort in trying to think carefully about what will be the proper solutions to help with those vulnerable communities. Yes.
What about existing onshore species like tilapia for onshore aquaculture? How is that going to do?
Yeah, so they will still be, they're still open to effects of climate change because they, and particularly, I think that's one aspect that hasn't been looked at a lot about how freshwater agriculture will fare under climate change. And I think that's very important topics because when we talk about agriculture, actually a majority of them are from land-based agriculture, and tilapia is one important wisely farmed species. So I think they are facing challenges such as the trade-off in terms of demand for fresh water, whether there are suitable water bodies to farm them, and also if people are thinking about using aquaculture to replace marine fish. I think in that particular paper that Eddie and our colleagues are involved in, we also pose serious questions about that idea because they don't offer the same nutritional values, particularly in terms of micronutrients, as for marine fish. And also, people who do fisheries in the coast may not have the capacity or may not even want to develop aquaculture, which is a totally new kind of activities for them. So I think there is, again, I think it will certainly play an important role in the future fish supply, but then how it would contribute to dealing with climate change challenge to seafood protection is another question.
Maybe one more question before hearing you all? Andrew?
Yeah, a sort of different question, but to what extent is fisheries governance starting to sort of recognize the changes that are going to be happening? I'm particularly thinking of allocation of, the few species that are managed multi-jurisdictionally. To what extent are these RFMOs and things like the Halibut Commission aware that over time the allocation formula needs to be renegotiated? Given these things take decades to do, are these organizations starting to think about these?
Yeah, I mean, I'm sure there are maybe the colleagues who is involved in the commissions that know much more about that. But based on my understanding, and my student Juliano have done some research on that because that's her thesis topic. It seems that there's not within the space that they have been thinking seriously for now, like either the tuna FMO or the bilateral FMO such as Pacific Halibut Commissions or the Pacific Salmon Commission. I mean, historically, they have been dealing with climate variability in the Pacific, so that's kind of an analog to climate change. But then the thing is that these changes may become more permanent and a much more bigger extent. I think these management bodies have not think seriously about that. And I think that's something that they should do and think about seriously. Because this change, as I show in my talk, that species changing their distributions and things like that are happening. And that it may be next year that some countries will demand for having access in the allocations of certain shared fish stocks. And if the management bodies are not prepared, they will be caught by surprise. That often lead to international conflicts that doesn't end well. So I think it highlights the need for these management bodies to think proactively, like starting to look into scenarios of what may happen, and then trying to see whether the current management systems is ready for dealing with this kind of surprise.
So please join us outside for some snacks and refreshments, and William will be there. You can ask him additional questions out there. Let's thank him once more.
Thank you. Hi.
Very good. Lots to think about.
Yeah, thanks.
The questions were about aquaculture. I'm not sure would do more with aquaculture.
Yeah, yes, because it's that's a big question that everyone is talking about. So